Swayam Prabha. Digital India. Educated India.
Till now we have studied nodal analysis with both types of independent sources. For current sources it's straightforward. For voltage sources we have to define a supernode and go ahead with the analysis. Now we will look at how to formulate nodal analysis equations when we have control sources. The first type of control source we will consider will be a voltage control current source. In fact, this will look very similar to a resistor. A resistor also can be thought of as a voltage control current source with the controlling nodes and the controlled nodes being shorted together. Okay, you have seen this earlier when we synthesized a resistor using a voltage controlled current source. Okay, but some features of the conductance matrix will be different from what we had when we had only resistors. So we will look at those things. A voltage control current source it's connected between some nodes. Let me call these node 1 and node 2, and the controlling nodes as node 3 and node 4. If there is Vx between them, the current between node 1 and node 2 will be Gm Vx. Okay. Now when I said it's similar to a resistor, this is what I meant. If a resistance is connected between node 1 and node 2 and the voltage difference between node 1 and node 2 is Vx, the current through the resistor will be G times Vx, where G is the conductance of the resistor. The resistance is R and the conductance is G. Okay, so you can see that between node 1 and node 2 a certain current is flowing that's proportional to Vx. In case of the resistor, Vx is the voltage between nodes 1 and 2. In case of a control source, Vx is the voltage elsewhere in the circuit. Okay. What I have put down here is the general structure of the nodal analysis equations for a resistor. Okay, I will fill in the entries. What I have is that the equations, as you well know, is conductance matrix G times the unknown vector V equals the source vector I. Okay. Now I have shown node 1, node 2, etc. here corresponding to each row. You know that each row of this corresponds to one of the equations. The first row corresponds to Kirchhoff's current law at node 1, the second one to Kirchhoff's current law at node 2, and so on. Okay, up to node n. There are a total of n plus 1 nodes in the circuit. Excluding the reference node, we will have n nodes. And I've also shown these columns, and you know that the entry in this column multiplies V1, the entries in the second column multiply V2, and so on. So I've shown V1, V2, V3, V4 on top just for easy readability. Okay. Now let's see if a resistance is connected between nodes 1 and 2, what happens to it? How does it contribute to this conductance matrix? Okay. So there will be a current, and the voltage at node 1 is V1, the voltage at node 2 is V2. So the current will be G times V1 minus V2, where G again is 1 by R, and I have been saying repeatedly, sometimes it's convenient to use resistances in the formulation of equations, sometimes it's more convenient to use conductances. Okay. Now this current flows from node 1 to node 2. So obviously entries corresponding to this resistor will appear in this equation corresponding to node 1 and this equation corresponding to node 2. And secondly, the current itself depends on V1 and V2. So it will appear in this column corresponding to V1 and this column corresponding to V2. Okay. And we've already worked this out, right? You already know how to analyze circuits with resistors and control sources. So you know these things. I am trying to show in a general way how each resistance affects the conductance matrix. current flowing away from node 1 is G times V1 minus V2. So in the equation for node 1, we'll have G times V1 minus G times V2. Remember, this G will multiply that and this minus G will multiply that one. Okay, as I've shown on top. And the current flowing away from node 2 is G times V2 minus V1. Okay, remember, in each node, we group the currents which are flowing away from the node. So the current flowing away from node 2 is G times V2 minus V1, and we'll have G times V2 minus G times V1. Of course, in these columns and these rows, there will be other terms corresponding to other components connected to this node. Okay, but I am talking about now the contribution of only this particular resistor. Okay. Now let me take a different case where this was not node 1, but let's say node 4. Okay, and this would not be V1, but it would be V4. And the current, of course, would be G times V4 minus V1 flowing in that direction, downwards direction. So what would happen in that case? The resistance term would appear in the equations for node 4 over here and node 2 over there. The current flowing away from node 4 is G times V4 minus V1. So we would have G times V4 minus G times V2. The current flowing away from node 2 is G times V2 minus V4. So I'll have, instead of this G, I will show it in red. It will be G times V2 minus G times V4. Okay. The symbols shown in black and red represent two different cases. What I want you to appreciate now is the fact that in either case, right, you look at these four black entries, they are symmetric about the diagonal of the matrix. And you look at these four red entries, they are also symmetric about the diagonal of the matrix. Okay. So in either case, we will have a symmetric matrix as we've already seen. Now let's see what happens when we have a voltage controlled current source. So I have a voltage controlled current source here. It has a current flowing from node 1 to node 2, but the current itself is proportional to Vx, which is the voltage between node 3 and node 4. Okay, so this current is nothing but G times V3 minus V4. The voltage at node 1 is V1, the voltage at node 2 is V2, the voltage at node 3 is V3, the voltage at node 4 is V4. Okay. So how does this appear in the conductance matrix? First of all, the current is flowing from node 1 to node 2, which means that the equation for node 1 and equation for node 2, these two equations contain the term corresponding to the controlled source GM. Okay. So the current flowing away from node 1 is GM times V3 minus V4. So it will have GM over here and minus GM over there. Plus GM multiplies V3 minus GM multiplies V4. The current flowing away from node 2 is the negative of this. So we will have GM times V4 minus GM times V3. Okay. Now you see that in many ways this is similar to the resistor's case. The two nodes between which the control source is connected, their equations contain terms corresponding to the control source. But the important difference is that in general, these entries are no longer symmetric about the diagonal of the matrix. Okay. So when you have a voltage controlled current source, you can go ahead and write the node equations like before, except that the conductance matrix will not be symmetric. Okay. So that's the difference in general between these two cases. Now I'll show a particular example. Usually what I do is I show some particular examples and then generalize. In this case, I decided to do it the other way around because the resistor's case is so easy. I also wanted to show how the voltage controlled current source is similar to a resistor, but the only difference is that the entries appear asymmetrically in the matrix. Okay. So let's say we take a circuit similar to what we have been considering all along, but one of the resistors is replaced by a voltage control current source. This is I1, I3, R11, R33, R12, R23, and we have only 3 nodes in here, 1, 2 and 3, and let's say that this current source is Gm times Vx, where Vx is this one. Okay, so Vx is basically V2 minus V3. So first of all, it's obvious that this current source appears only in the equation for node 2 because it's connected between node 2 and the reference node. I have chosen the same reference node as I have previously done. Okay, so the equations for nodes 1 and 3 will be exactly the same as before. So if I write the equation for node 2, what will I get? The total current flowing out of this, which is the sum of this current, and that current, will be equal to 0, which means that the first one of them is V2 minus V1 times G12, and the current through Gm is basically V2 minus V3 times Gm, and current through this is basically V2 minus V3 times G23, and the whole thing equals 0. Okay, and if I group the coefficients of each variable together, I'll have V1 times minus G12 plus V2 times G12 plus G23 plus Gm plus V3 times minus G23 minus Gm equals 0. Okay, so this is what I'll have. Now let me write down the entire conductance matrix. I'll copy this circuit over. As I said, the equations for node 1 and node 3 are exactly the same as before. So I'll have G11 plus G12 over there, minus G12 there, and 0 for the first row, and for node 3, G23 plus G33, the total conductance, minus G23 over there and 0 over there. And of course the special case is node 2, which gives you minus G12, and for this we'll have G12 plus G23 plus Gm, and the last one will be minus G23 minus Gm. Okay, so it's still of the form G times V is I, and this G matrix contains the conductances and the transconductances, or the coefficients of the voltage controlled current sources in the circuit. Okay, and also you can see that the structure is not symmetric. But other than the fact that the G matrix is asymmetric, it's not very different from the case of having only resistors. Okay, so it turns out this is the simplest of the control sources. For other control sources, we will have to do things like we did in case of the voltage source, using super nodes and so on. Okay.